Hello, and welcome to Module 0 Revision. The purpose of this module is to revise some important points related to digital logic design, particularly timing and the actual design process itself. Hopefully you did cover this as an undergraduate, but I know it was a while ago, and these are some of the more advanced concepts in digital design. But before I do that, I want to talk about the general revision points that I'd like you to cover in addition to what I'm covering in these notes. In this course, I do expect you to be familiar with combinational logic structures, including the different types of adders, multiplexers, and so on, and of course the basic logic gates. I expect you to be familiar with combinational logic optimization, particularly Carnot maps. I will revise in this section and the timing notes, flip-flops and latches and their operation. You are expected to know how to produce a timing diagram and how to use one in design, and that is actually the main point of this section. It's worth revising how finite state machines work, though I will revise that when we get to the section on how to code them, similarly for counters. But most importantly, I expect you to be able to design a simple logic function at the logic level, not at the RTL level. That's what we're covering later in this course. For example, I'm going to have a section later illustrating that, and you're going to do a similar example in the first homework. There are numerous books on digital logic design authored by people such as Katz, Wakely, and Mano if you need more revision. So most digital systems are synchronous, and all the digital systems we're dealing with in this class are synchronous. That means that there is a master clock fed to all the registers. For the purposes of this set of notes, one clock only. And edge-triggered flip-flops are triggered by this master clock to synchronize all logic. And also it's useful to think of these flip-flops as storing those logic values between clock periods during which logic is re-evaluated. But let's just deal with the flip-flops first. So on the right, I have a symbol for a D flip-flop, a positive edge-triggered D or data flip-flop. And the basic function of the flip-flop is as described in the box. That is, after a 0 to 1 transition of the clock, Q becomes D. That is, Q takes on the value of D present just before that transition, but note, Q does not change until after the clock edge is complete. In this class, we'll be using a lot of registers. Registers are simply groups of flip-flops, normally indexed by some sort of value, as shown on the example on the bottom right. So I can use a simple flip-flop to illustrate the concept of a timing diagram. Timing diagrams are a very useful tool for analyzing synchronous digital designs, and I strongly encourage you to draw timing diagrams of your design intent before going off and simulating RTL. A very important debugging tool for you will be matching your expected timing diagram against that actually produced by the tool. So here's a simple timing diagram just for a D flip-flop. I have the clock at the top. I've extended down the positive edges of the clock, which are the synchronizing events. I have the data D input, and I'm going to illustrate Q at the bottom. Initially, in the simulator, Q will be unknown, don't know, don't care, or X. This is represented differently in different timing simulators, but initially in Verilog, all variables initialized to unknown or X. On the first rising edge of the clock, Q becomes D after that rising edge, so Q becomes 0 a short period of time after the rising edge of the clock. Here I've drawn it with a slight delay, as would happen in the actual logic from the clock edge. In RTL, it will actually be falling on the clock edge. On the next rising edge of the clock, D is resampled. At this point it's 1, so Q becomes 1 after the rising edge. Then you notice that there's a glitch in D between rising edges of the clock. These glitches occur as the logic that feeds D is evaluating what should appear at D due to the different delays in the logic chain. But note that these glitches do not appear at the output. That is one of the beauty of these synchronizing events. They only sample the production of the combinational logic on the rising clock edges. So on the next rising edge of the clock, Q stays at 1, and on the final rising edge of the clock, D has fallen to 0 beforehand, so Q falls to 0. And of course, the key principle of the operation is after each rising edge of the clock, Q takes on the value of D that was present just before that clock edge. So now that we've covered just flip-flops, we're actually more interested in general logic. So here I have a simple logic design consisting of 2 stages of flip-flops. In this example, I have not named the outputs of the first stage of flip-flops, though in RTL coding you do have to do that. There's combinational logic in between these 2 stages, and the final output of the second stage is called out. I want you to remember a couple of things here in this type of logic diagram. The basic principle of operation is that on one clock edge, in gets transferred to the output of this first stage of flip-flops. Then in between the clock edges, the logic evaluates to determine what's going to be presented at the next stage of flip-flops. On the second clock edge, the logic at this point is transferred to out. At the same time, the next value of in is presented to the outputs of the first stage of flip-flops. So simultaneously, throughout the whole logic design, on each rising edge of the clock, all the register outputs become equal to the register inputs. And the idea is before the next rising edge of the clock, all the internal logic has re-evaluated to present the next values of the inputs to the flip-flops to be resampled. I think it'd be useful to you to actually pause this recording and see if you can produce this timing diagram based on your memory of how synchronous logic circuits work. Okay, well now you've produced that timing diagram, or you chose not to, and I will present the solution before showing how some of this can be calculated. Of course, before the first rising edge of the clock, we don't know what out is. In fact, even after the first rising edge of the clock, we don't know what out is. It takes 2 clock cycles, and this is important to realize, it takes 2 clock cycles for a change in to affect the change in out, because there's 2 stages of registers in between. So after the second rising edge, the value f that was presented at in on the first rising edge, that got presented to the combinational logic. Combinational logic evaluated that, producing f. As they're OR and AND gates, so if you have 1, 1, 1, 1, you're going to get 1, 1, 1, 1. And then on the second rising edge of the clock, out becomes equal to f. Now notice at the same time, 1, 0, 0, 0, 1 has now been transferred from in to the output of this first register. That is evaluated on the next clock cycle, and you perform the appropriate AND and OR operations, and you'll get 0, 0, 1, 0. Same time, A, 1, 0, 1, 0 has been transferred from the input to the output of the first register. Next rising edge of the clock, that gets evaluated by the gates, producing back A, which then becomes an out on the next rising edge, and so on. We get A again from the 5 input 2 clock cycles ago. So I hope you got that answer. If not, you should look at the next slide before going off and rethinking how you're doing this. So this is an animation of just one of the stages of logic evaluation. Here I'm starting before this rising edge here, the 4th rising edge, where 5 is being presented at the input in. After that first rising edge of the clock, 5 is transferred to the output. 0, 1, 0, 1 is now at the input of the combinational logic. The combinational logic takes a little bit of time to evaluate, but its evaluation is completed before the next rising edge of the clock. If you do the logic operations, 1 and 0 is 0, 1 or 0 is 1, 1 and 0 is 0, 1 or 0 is 1. The output of the combinational logic, which is now being presented at the second register, is 1010 or A. Thus, after the next rising edge of the clock, A gets transferred to the outputs of that register. Now let's look at an example with feedback. Here we have a feedback path coming from the output to the logic being evaluated. This is perfectly fine as long as that feedback comes from the output of a register, not from internal into the logic. I'll talk about that again later. Now in this example, in the previous example, I had the output starters don't care. Can we do that here? Can we actually evaluate this if out is unknown at the start of the simulation? Of course, the answer is no. We do need to have some starting value of out. And later in this course, I will discuss the importance of having a global reset signal to initialize all registers. But we're not covering that in this part. So we need an initial value for out, and it's 4. Now again, there's 2 stages of logic. So it takes 2 clock cycles for a change of in to influence the output out. And of course, it's important to remember that both registers are operating in parallel. That is, on every rising edge of the clock, the input of the register is transferred to the output of the register. That output changes just after that rising edge. So again, in this example, it's going to take 2 clock cycles for the data value A at in to influence what we see at out. Hence, down here, you don't see out changing on the first rising edge. So the question is, what will it be on the second rising edge? I suggest that you evaluate this. This is just simply A appearing here with the 1 from out being 4 appearing there. If you do that logic evaluation, and I'll show an example on the next slide, you end up with 4 being produced by those muxes. They will be at the output of those muxes at this point here. Then on the rising edge of the clock, 4 will be transferred to out. Next cycle, 1 is evaluated by the combinational logic. Out 2 is still 1. You evaluate how those muxes perform, and you'll get 0 at out at the next rising edge. Similar evaluations when B is on in, 2 cycles later, 1 will appear on out. When 5 is presented, 2 cycles later, 3 will appear on out. Again, let's take a snapshot of this and animate this so you can see what's happening internally. So, A is presented before the first rising edge of the clock on in. On the first rising edge of the clock, that value of A gets transferred to the Q outputs of that first register. Out is 4 at this point, and it stays 4, it hasn't changed, and that's actually an assumption here. And thus out 2 is 1, so it's presented that XOR gate. The XOR gate has 1s on its inputs, so the output of that XOR gate is 0. So the top input of each of these muxes is selected. If you look at what's connected to the top input of each of those muxes, it is 0, 0, 1. By the end of this first clock cycle, that the combinational logic has evaluated, and the result of that evaluation is being presented to the D input of the register out. On the next rising edge of the clock, that gets transferred to out. So it happens that the value stays at 4. And you keep doing this evaluation over and over again, and you can work out what's happening in this particular example. I mentioned earlier that this is something you shouldn't do, and here we're going to discuss briefly why, and that is you should not do combinational logic feedback. That is, in this bold line here, we are feeding back combinational logic from a combinational logic output internal to the logic block to a combinational logic input internal to the logic block. What is wrong with this? Now, to illustrate this, what is wrong with this, I've put this particular set of values here where the Q outputs of the first register have 1101 on them, and the output of that bottom mux has 1 on it. This is going to cause a problem. What's that problem? Well, if you think about it, what's going to happen is the logic at the point star, which is here, will oscillate. You'll go 1 0 1 0 1 0 1 due to this feedback loop that you've created internal to the logic. And the period of that oscillation will not be the clock period because it's not going through register. It'll be whatever the natural delay is of the logic gates in this loop. Thus, you cannot predict what value will actually be presented here at the end of the clock period. It'll actually vary with temperature and vary from chip to chip due to process variations. So this leads to unpredictable logic behavior, and that is why you can't do this. And by the way, in coding RTL, it is common to accidentally do this, so that is unintentionally create combinational logic feedback. We'll be talking about that later. So that's the VAT point. You don't know what the value of out2 will actually be. So thus, in general, digital systems are built as a collection of registers with combinational logic between them. And again, the basic principle of operation is all the registers sample their inputs at the same time at the rising edge of the clock. Then before the next rising edge of the clock, all of the combinational logic blocks evaluate what appears at those Q outputs to determine what's going to appear at the D inputs before the clock period is over. Note, the combinational logic cannot store data. The only data that is stored, that is preserved from clock cycle to clock cycle, is that is stored in registers. This is in fact how you actually decide what registers you need. What data states do you have to preserve between clock cycles during which you reevaluate those data states. We have a mux here producing next B, and select B, cell B, is actually a control line coming from the controller manipulating that mux. And this is actually a fairly common construct, and we'll talk about this more later. Notice there's a 0 flag being produced here. B is being monitored. If it's equal to 0, this line labeled 0 goes high. This is the status line going to the controller. We'll be talking about separating data and control paths in a few classes' time. Here's another example of something that is wrong. I get students often asking if they can do something like this. And I want to point out this, actually, though it's technically doable, it is very tricky to execute well. And thus, I don't encourage it. And that is, hey, can I have a logic path that I can tell the synthesis tools takes 2 clock periods to evaluate, and thus I can make it slow? And the answer, and this is not possible to do. This is very difficult to do. And the reason is given at the bottom here. And that is, and as we'll talk about this more in the timing notes, that logic delay is actually very hard to predict. It varies enormously across the possible process variations in the factory, which give roughly a 4-to-1 range of delay, and across a temperature range at which the chips could operate. If you're relying on this logic, taking actually between 1 and 2 clock periods of delay to operate, and it must take more than 1 clock period in order to work correctly. And then you take the chip to Alaska and operate in Fairbanks outside in the middle of winter, which you have to guarantee that the chip can do, it most sure won't work. The logic will operate too fast, because in CMOS logic, it gets faster at cold temperatures. So because it is very hard to actually predict the delay of combinational logic, well, more precisely, you can predict it, but more precisely, it has a very wide range. It's very difficult to design a piece of logic that you can guarantee will always take more than one clock cycle to operate. Thus, I don't encourage you to do this, though there are features in the tools that enable this under certain circumstances. So next we're going to turn to a sample design problem. So we looked at timing diagrams. I want you to understand how timing diagrams are done. And now we're going to do a simple design example to start getting you doing design. I'm going to design a simple 8-bit adder accumulator with the properties as discussed here. We've got a control signal coming in, accumulate. When that is high, whatever's on the input in 1 is added to the current accumulated total and appears on accum out. You're going to use absolute, that is unsigned numbers. When clear is high, another control input. And to make it clear, accumulate will be low. We're going to clear the contents of this register. And I want an overflow flag that goes high as the adder overflows. And so one thing you have to work out, of course, is how you're going to produce this overflow flag. Well, I'll remind you that an 8-bit adder actually produces a 9-bit result. The 9th bit being the carry out of the adder, the other 8 bits being the 8-bit sum. In Verilog, this is written as shown on this page, and the details here don't matter, we'll come back to this later, but the point is I'm reminding you that an 8-bit adder produces a 9th bit result, the carry out. And of course, with unsigned numbers, how do you detect an overflow? If this carry out becomes equal to 1, that means you've overflown. So at this point, I think it'd actually be useful for you to stop this recording and actually try this design example. Now that you've tried it, let me show you what I did. So what I'm going to do is produce a sketch of this design. I'm going to talk about the steps in doing this beforehand. The first step actually is just to identify some of the inputs and outputs. But the first important step in the design itself is to determine and name all the registers. What has to be registered? What data values do we have to preserve between clock cycles? Do we have to carry over from clock cycles? Here, there's only one data value that has to be preserved from clock cycle to clock cycle. And that is the value of accumulate out. So I need a register whose output I call accumulate out. And I have to name all registers, because when I write my RTL, I'll have to name them there. The next step is to determine the combinational logic. That is, how will the inputs and internal values be re-evaluated every clock cycle to be presented at the D input of the register. The core of this combinational logic here is a selector or multiplexer. Why? Because on the previous page, I specified a set of alternative actions that take place in different scenarios. If clear is high, clear the register. If accumulate is high, add into the register. And obviously if both are low, accumulate out stays the same. So the key piece of logic I need here is a multiplexer. Now all I have to do is work out the inputs to that multiplexer. And these are those inputs. So what are the inputs I have here? Remember, if clear is high, I want 0 to go to accum out. So I need a 0 input. If accumulate is high, I want to add in to the current value of accum out and present it to the input. So here I've drawn an adder, and I remind you that the 9th bit of the adder is the carry out, which I'm going to relabel as the overflow. And finally, if clear and accumulate are both low, I want to keep the current value of accum out. The way I've presented this in this design is this feedback path here, where accum out is presented back as a third input to this mux. Now you might be saying, wait a minute, this mux has 2 control lines and only 3 inputs. Well, what about the other 5 inputs? This has to be what about the other input? This has to be a 4 input mux. And the point is, yes, if you're designing this as actual logic, you'd have to work out what that 4th input, the mux, would be. And by the way, that would be when both clear and accumulate were high, and I didn't specify what actually happens there because I said it would never happen. So it actually wouldn't matter what you made that 4th input. But the point is, really, that though in homework 0, I want you to design all the logic down to the bit level, in general, we don't have to do that when we're specifying RTL. This level sketch is enough information for us to go off and start coding, which of course we'll be doing in a later class. Other suggested revision points, I put this on the first page. I want to remind you here, you should remind yourself all the basic logic gates work, remind yourself what the truth tables are and how they're manipulated, remind yourself how Carnot map optimization is used to produce minimal 2-value logic, and remind yourself the basic operation of finite state machines, though this is one aspect we will come back to later. So that brings me to the end of this section. What I'll remind you is the overall basic operation of synchronous logic. On each rising edge of the clock, all the register inputs get transferred to the register outputs for all the registers at the same time. In between the rising edges of the clock, the combinational logic paths evaluate to present the next set of inputs to those registers. And in this example, we have 2 combinational logic paths. And here I actually show some feedback and feed forward. And again, it's important to note that the feedback comes from the output of the later register. It is this basic principle of operation happening each clock cycle all over the chip, where all the logic is operating in parallel, that actually gives digital logic such a high level of performance. It has huge levels of microparallelism, and we'll again be talking about that later. So I thank you for your attention in this set of notes. You should now go on and do homework 1, which consists of 2 components, the quiz in Moodle and a written homework which is a design example to also be submitted.